Hello class. So we'll continue on section 5.2 on this video. In the previous video, we saw that we have all these properties of integrals, namely 6 of them. Most of them were pretty straightforward. There were 2 of them that you kind of have to think a little bit about how they work. And one of those 2, the first one, I don't see how it's intuitive. You just have to kind of memorize it. That's what happens. Okay. So now we're just going to do an example that uses these properties. So suppose that the definite integral from 1 to 4 of f of x dx equals 8. That means that we don't know what function f is. Since this integral exists, it has to be continuous, right? The integral exists. It's the same as saying that the function is continuous. Doesn't matter what f is. We know that the area bounded by f, the net area is 8 on the interval 1 to 4. Similarly, on the interval 1 to 6, the net area bounded by f is 5. Now, given this, we should be able to answer the following questions. Find the net area on the interval 1 to 4 of -3 of f of x dx, and find the net area on the interval 6 to 4 of 12 times f of x dx. If we can do both of these examples, every example like this is kind of like the same. So let's start with A. So we want to rewrite this in a way that we can use either this information or this information. How are we going to do that? Well, we're going to do it using properties of integrals. For example, one of the properties we saw before, and that was the same for indefinite integrals, is that whenever you have a constant, so this is property 4, whenever you have a constant multiplying a function, you can move it outside the integral. Meaning that this -3, we can move it outside. So it's the same as -3, that's the integral of 1 to 4 of f of x dx. Now, this we know what it is. This was given to us to be equal to 8. So if we plug that in, this just becomes -3 times 8, which is -24. And again, it's fine that it's negative because this is net area. All it means is that the area below the x-axis is more than the area above the x-axis. So this one is kind of straightforward. Just use the constant property. So you can move the constant outside. The next one is a little bit harder. So what's B? Here we have to use a couple properties at the same time. So if the integral, not from 4 to 6, but from 6 to 4 of, 12 times f of x dx. Okay. And again, we want to rewrite it in a way that uses this information that I underlined in red. This and this. So how are we going to do that? Well, you can always simplify a couple things. Immediately, whenever you see a constant multiplying the function, just move it out. So this is the same as 12 times the integral from 6 to 4 of f of x dx. Now, another thing, the integrals we're given here, they're all, the lower bound is always smaller than the upper bound. Right? In the integral we're given, we have the order flipped. And this is where you can use that kind of weird property, which was property 1. You can always flip the bounds of the intervals, this a and b. You just have to add a negative in front. What does that mean for us? If we add a negative in front, we can change the order here. So instead of writing from 6 to 4, we can write from 4 to 6. Now that looks closer to what we need. Unfortunately, it's still not all the information, right? Because what information we know. We know what is the integral from 1 to 4, and we know what's the integral from 1 to 6. Here, trying to find the integral from 4 to 6. How can we do this? Well, look at this trick. Again, it's using properties of the integral. Okay, the integral from 1 to 6 of f of x dx. Right? Using property 5, meaning that you can break this up into smaller subintervals. Right? We can rewrite this as, well, the integral from 1 to 4. So I'm first calculating the net area on the interval 1 to 4, and then I calculate the net area on the interval from 4 to 6. That's what property 5 says. You can break up the integral into smaller intervals. Now, why is this useful for us? Well, because we're given what this is. If we look back here, that integral is 5. So this here is 5. This is kind of like what we're trying to find, and this we're given. Why? Because we're given that the integral from 1 to 4 of f of x dx is 8. So this part is 8. So plugging everything in, what do we get? We get that 5 equals 8 plus the integral from 4 to 6 of f of x dx. Well, move 8 to the other side, and what do we get? The integral from 4 to 6 of f of x dx equals, well, 5 minus 8, which is negative 3. Finally, plug this into our work above. So let me box this off. Well, going up from our work above, this thing here is the same as this thing here, which we found is equal to negative 3. So just plug that in. This is negative 12. All this thing here is negative 3. So times negative 3. That's negative 12 times negative 3. That's 36. So this example kind of uses a lot, well, 3 or 4 of those properties. So if you can understand this example, you can understand the other ones. So definitely, I would focus in this video, I would focus, so this example is kind of trivial. You just move the constant outside, but it kind of teaches you how to substitute the value of a definite integral. Right? This whole thing we know is equal to 8, so we substituted that in. This one is definitely harder. Think about what we did. So we started here. Then we did some steps here to simplify some things, and then we ended up here. So think about how we did this, and hopefully that gives you an idea how these properties are used. If you have any questions, you can always ask me.